Okay, so we're going to look at the required homework problem that is associated with concept 2A in your required homework, in your chapter 2 concepts. So this is the graph you're given, and you're given a series of questions about that graph. So the first question asks us, during what time period is the object standing still? Now, whenever we're assessing a graph and assessing how graph describes motion, we have to first make sure that we know what the graph is talking about. So what are the axes? What is the graph representing? And we can see in the example that we have position over time. So this is a position versus time graph. So to represent an object standing still with position, that means the position isn't changing. So we want to examine where the position isn't changing, where the position is, as time goes on, the position is maintaining its value. So that's a flat horizontal line. So during this time frame, the position is not changing its value as time goes on. And during this time frame, the position is not changing its value as time goes on. So those two positions, or those two time points, excuse me, are between 6 seconds and about 9 seconds. So 6 seconds and 9 seconds, and you can look at your own graph because I didn't put axes on here. And again, starting at about 14 seconds to the end of the graph, which is about 17 seconds. Okay, so that's our position that isn't changing. So part A, which is when the object is standing still. All right, part B said, when is the object at the origin? Okay, well, the origin means the position is equal to 0. The object is never at 0. If this is our 0, 0 mark, and again, on your homework sheet, you should be able to see that time, that axis designation, and the object is never at 0. So the object is never at the origin. So for part B, never is the object at the origin, given our graph. Good. Part C says, during what time period is the object accelerating? All right, so from a position versus time graph, that acceleration is going to look very specific. So let's think about what acceleration means. It means that the object is getting faster and faster and faster, or slower and slower and slower. It's changing its velocity. It's changing its rate of moving. So if an object is getting faster and faster and faster, as time goes on, the position the object changes gets bigger and bigger and bigger. If an object is getting slower and slower and slower, as time goes on, the position that the object is changing is getting less and less and less. So is there any time during this graph where the position is changing, is getting bigger and bigger and bigger? All right, so let's look at the beginning of the graph. So here we see that position changes a little bit as time goes on, then a little bit more as the same time goes on, then a little bit more as time goes on. And during this phase, the object's position is changing more and more as time goes on. So during this phase of the motion, we have an acceleration. We have a change in that motion. So we can see that for part C, from time equals 0 to, it's about 6 seconds, the object's accelerating. And on a position versus time graph, acceleration looks like a curve. Okay. All right. When is the object accelerating? The same sort of question for part D. And is it speeding, when the object is accelerating, is it speeding up or slowing down? That's what it's asking. Okay. Well, as the object is changing its position by more and more and more each time, it's speeding up. So if it's going faster and faster and faster, it's going to change its position by more and more each time. So in this case, it is speeding up. Now, there are other ways to also examine this. We know that the velocity is the rate of change of the position. So our velocity is the slope of the position versus time graph. We know if our slope increases, our velocity increases. And if I look at the slope of this position versus time graph, I see that it is increasing and increasing. If we look at that sort of tangent straight edge representation of the slope with the eraser. So my slope is increasing, therefore I'm getting faster and faster and faster. I'm speeding up. All right, when is the object moving in the negative direction? Okay, we want to keep in mind that this means that the position is going from a far away from the origin, or farther away from the origin, towards the origin if I'm on the right side of the origin. So I'm moving in the direction of negative position. I'm moving in the direction, if I'm on the right side of the origin, which I am. I'm on the positive side of the origin. If this is the origin, I'm to the right of it. I'm in positive values. I'm moving towards the left or towards those negative values. And that happens during this part of the graph. So I'm at some velocity that is more positive, and some position, and as I change, as time goes on, I'm getting closer and closer to the origin and I'm on the right side of the origin, and so I'm moving in the negative direction. So that happens between time equal 9 seconds and 14 seconds. Okay, and at what point does the object turn around? All right, so turning around means we're going from one direction to the other direction. So if I'm moving in the positive direction, I move to the negative direction. If I'm moving in the negative direction, I've changed and moved to the positive direction. So if I look at the graph as it progresses, I'm moving in the positive direction. My positions are getting further and further away from the origin in the right side of the world. I'm moving in the positive direction, then I'm standing still, and then I start moving in the negative direction. So I would argue at this point, we get the turning around. So part F is at 9 seconds. All right, so those are all the questions relating our position versus time, getting a little into the details of what that graph looks like. Good job.